Can you hear me, Patrick?
Yep. Hi, everyone. Thanks for joining this NASA Google Plus Hangout. We're here to talk about climate change with 4 NASA scientists and also the major IPCC report that just came out on Friday. Just want to remind everyone how you can participate today. If you want to ask questions, you can ask them in the Google Plus comment section. You can ask them in the YouTube comment section if you're watching it there. Also on Twitter using the hashtag #AskClimate. I'm Patrick Lynch. I'm with NASA's Earth Science News team, and let me go ahead and introduce our panelists today. At Goddard Institute for Space Studies in New York, we have Drew Shindell, who's coordinating lead author of one of the chapters in the Physical Science Basis Report for the IPCC, and also a drafting author of the Summary for Policymakers. At Goddard Space Flight Center in Greenbelt, Maryland, we have Ralph Kahn, who's a reviewer on the aerosols chapter. At Jet Propulsion Laboratory, and also a faculty member at UC Irvine, we have Eric Regnault, contributed to the cryosphere chapter. And in Hampton, Virginia, at NASA's Langley Research Center, we have Bruce Wilicki, who contributed to, or was a reviewer on several of the chapters in this report as well. So the IPCC report is the benchmark climate change report, and gives us a sort of fundamental understanding of the state of climate change science, and only comes out every 5 or 6 years. So on Friday we got the summary of the latest version of that. And Drew, since you were just in Stockholm, well, it appears you might be on mute, so maybe I'll wait. Can you hear me, Drew? Okay, well, maybe we'll go off. Ralph, as you were a reviewer on it and obviously of following it, before we really dive into it, I wonder if you could just give me a sort of big picture overview of some of the key points of the report.
Well, I want to start by saying something about the process, because I think that's an important part of what this document represents. There were over 1,000 scientists who participated one way or another in either writing or editing or reviewing the multi-thousand pages that are involved. The material, of course, is very complex because we're dealing with the climate, so we have experts in a great variety of areas, and as you can see from the 4 of us here, experts in a variety of different things. And then there are many more. There are people who are experts in land surfaces, there are economists and people who do predictions of how society is going to respond or react over in the future in terms of their use of energy and so on. It's an effort that took more than a year, and it involved writing a first draft, having a set of reviews, writing a second draft with responses to tens of thousands of comments from the reviewers, and then the second draft was reviewed again by government officials primarily from about 85 countries, and that's the report that we have. It represents a consensus.
Bruce, I wonder on the sort of major benchmarks that we think about when we think about climate change. What were some of the changes from the previous report to this one, or if there weren't necessarily changes, even if they were subtle, you know, what did we put down on paper as sort of what we understand as far as how much the globe has warmed and how much we expect it to, given in the range of scenarios going forward in the next century?
Yeah, I think in this new report we've gotten a longer climate record than we had before. We've added quite a bit of information, and I'm sure we'll talk about this later on how ice sheets have responded. That was totally missing in the previous report because our level of understanding was so poor. I think we've also looked very hard at validating the climate models, trying to understand how accurate they are and the past data versus the predictions of what we would expect. There have been some people really angst kind of about what you see in the media called the hiatus, where warming of the last decade has slowed a little bit, but that's really kind of within natural variability or noise in the climate system. So we really tend to look at more like 50 to 60-year time scales to understand what the climate system is doing versus our predictions of it. And this report is, again, focusing on not just any one climate variable like temperature, but everything from precipitation, water vapor, deep ocean temperatures, everything in the system, basically.
Right. Okay. Eric, on this question of what sort of changed from the previous report to this one, it seems like one of the major changes that has occurred was in a sort of better estimation of potential sea level rise, and I think some of that was being able to sort of better estimate the response, of glaciers and ice sheets. So I wonder what your thoughts are on what changed from the previous report to this one in terms of what we were able to say about ice sheets, glaciers, and what they may contribute to sea level rise.
Yeah, the report summarizes all the advances that have been done since AR4. So the report started almost 5 years ago, where the thousands of scientists that Ralph mentioned in the beginning get together and look at the latest research and make an assessment. It's important for the audience to understand that a lot of the conclusions that are reached in the report are the summary of multiple lines of evidence, multiple lines of research converging to the same answer. The report is an update since AR4, and Bruce emphasized a very important point. It's that we have a longer time record now. We have 5-6 years of additional data. And for instance, in terms of looking at changes in the polar regions, we have increased confidence in our observations because of the longer time record. And some of the changes in the polar regions, snow covers, sea ice, ice sheets, in this report are larger than what we had in AR4. So it's sort of more difficult to ignore these changes because they're so big. In terms of the ice sheets, observations have improved, like I just said, in terms of characterizing what the ice sheets are doing. I think in this report we recognize also that a lot more work needs to be done before we can quantify what the ice sheets might do in the future. And this remains a large source of uncertainty for future sea level rise. The models have improved. They've improved mostly because they can be confronted to more observations, but there's still quite a long way to go before we can say with good reliability what the ice sheets are going to do, what the glaciers in Greenland and Antarctica are going to do in a warming world. A lot of what is in the report is a consensus, is some sort of compromise between all the recent studies. It may not mean that what is in the report represents necessarily extreme scenarios in sea level rise.
So the report, if you're looking at the different scenarios, I think it gives a range of about 11 to 38 inches of potential sea level rise by the end of this century for people in around the world, and in the science community that's about 28 to 97 centimeters. So in the previous report, we weren't able to give this estimate or what people thought was an accurate estimate because of our present understanding of ice sheet response. How far is there to go until you feel like there is a really full understanding of that response in order to make that number or that projection as accurate as possible?
Well, Patrick, that's a very difficult answer. I think the main achievement of this report is to recognize that we still have a lot of uncertainty in the models that represent ice sheets. There's a lot of uncertainties about how fast glaciers can flow around Greenland and Antarctica, how fast they're going to respond to ocean warming and warming in air temperatures. I think collectively we've realized that that response might be larger than what models have been able to replicate so far. So a lot of the basis for projection for sea level, including the contribution from ice sheets, somehow should be seen as a conservative scenario. Ice sheets respond to climate forcing in what we call in a non-linear way. If you warm up the climate, they start melting. There's absolutely no doubt about that, in a warming climate, the ice sheets will continue to melt, and they will do that for centuries to come. But as you warm the system more, they can respond even faster. And we don't have enough observations and understanding to tell you exactly how much faster they're going to respond, how much faster the glaciers are going to flow 20, 30, 50 years from now. But from what we've seen for the past 20, 30 years of observations from satellite is that that response is more likely to be larger than what the models are estimating now than smaller. The reason why this is so complex is because ice sheets evolve in concert with the whole climate system. They are affected by the ocean, they are affected by the atmosphere, and in order, and they have their own internal dynamics. So in order to really come up with good scenarios of evolution of these ice sheets, we will have to have a good handle on all this system. So it's not an effort involving just glaciologists like me, but involving the whole climate modeling community at large. And we're getting there, but it's going to take a little while longer.
So I'd like to make a point here, which is that the IPCC process has tended to be dominated by modelers who model the climate, because models are the only way we know to make predictions. However, there's also the measurement component, which is extremely important, because the only way we know that the models are telling us what's actually going on, that they're accurately representing the processes involved, is by making measurements. And so one of the things we've seen, since Patrick was asking about how things have advanced since the last report, which was about 7 years ago, is in the area of measurements. For example, if you compare the estimates of forcing uncertainty between the previous, what we call AR4, and the current AR5, you'll see that the direct effect of particles in the atmosphere has gone from a relatively high uncertainty to a lower uncertainty, which is more confident. And that's because of measurements that we've been making with NASA satellites. There are still some uncertainties, but the level of understanding that we feel we need in order to contribute quantitatively to validating the models is now within reach, although it's not yet within grasp. On the other hand, particles in the atmosphere, which would be wildfire smoke, desert dust, urban pollution, volcanic ash, those particles also have what we call an indirect effect on clouds. And this is a very important process, because to make a cloud particle, you have to collect water vapor molecules from the air. And the most common process by far for doing that in the Earth's atmosphere is to have a particle that tends to attract the water molecules and forms the cloud droplets. And so the presence and the nature of particles in the atmosphere is an important factor in determining clouds, and clouds then are very important in mediating the planet's energy balance. And one of the new things in the IPCC AR5, this new report, is that there is a chapter that deals to a large extent, for the first time, with the aerosol cloud interaction issues. That area is one which is in its infancy, and our ability to model aerosol cloud interactions is extremely primitive at this point. However, the fact that we now have a chapter that deals with that question is a real advance, and the next report in 5 to 7 years hopefully will have the improvements that we've been able to make by the combination of better measurements and then the implied improvements in models.
Okay, great. We have been having some technical difficulties in New York, but Drew, I think you may have been able to join us now. Can you hear us, and can we hear you? You can hear us, but we can only see your lips moving right now, so I guess keep working on that, and we'll try to get back to you soon. Ralph, you were just talking a little bit about the certainty that we know this with, and for either you or Bruce, so I know you.
The uncertainty, and I think Bruce was here too.
Right. One of the things that sort of got attention, I guess, it was maybe an incremental change in semantics in the way we talk about this, was that we go from 90% certain that human activity is driving most of the warming we've seen since 1950 or so to 95% in this report. Bruce, is there any, is that a material change there, or is there?
Yeah, that's definitely a material change. I mean, one way to think about it is that you've cut in half the possibility that you were wrong from 10% to 5%, and every time you do that, I mean, if you look at solid-state physics like the Higgs boson, where they're trying to determine when they know they have that particle, they're trying to drive that uncertainty to very small amounts. And in climate change, we're trying to do the same kind of thing as scientists, to be more and more certain about what we know. And I think in the things you're hearing us talk about uncertainties, you've heard about the ice sheets, you've heard about the aerosols. The other thing we're working on a lot is the uncertainty in climate sensitivity. You can think of this as kind of the volume dial on the climate system. So for the amount of CO2 we have in the atmosphere, and how much warming will we get long term in the planet, which will then further affect things like ice sheets and sea level, agriculture, everything else. That volume dial setting is still uncertain to a factor of 2.5 with about 66% confidence. And so then if we ask for 90% confidence, it's more like a factor of 4. So those are the kind of things that we need: longer and longer data sets, more and more accurate data sets, better theory behind some of the physics like aerosols that Ralph was just talking about, or glaciers that Eric was talking about. And the other thing, and that's the wild card in climate sensitivity, is the clouds. And clouds in particular, low clouds, are the ones that are kind of the wild card. They reflect sunlight back to space to cool the planet. They don't have a lot of thermal blanketing in the infrared greenhouse because they're so low. They're a similar temperature to the surface. But we're also working very hard to kind of improve understandings of what we know about climate sensitivity as well. And when you put all those together, how we're forcing the system, what its sensitivity is, and how the ice sheets and sea level will respond, that's where you get a much better sense of narrowing future uncertainties 50 to 100 years from now, tighter than we currently have them. So every IPCC report is trying to push the envelope of what we know and make it more accurate, so society can make more intelligent decisions on where we go.
So let me just add one thing to what Bruce was saying. What he means when he says the volume knob is being turned. The issue there is, if you...
I cannot talk right now.
We're changing the composition of the atmosphere by adding CO2 and other greenhouse gases to it. And the question is, if you add a certain amount of CO2 to the atmosphere, how much of a change in surface temperature will occur? And that's the uncertainty that Bruce was talking about. And one of the other new things in this new IPCC report is there are a few little sections on something called geoengineering, which are attempts that ideas that people have to try and deliberately make changes to the climate by doing one thing or another deliberately, like putting sulfuric acid particles into the stratosphere, or making the clouds brighter by adding particles to them. And one of the big uncertainties, as Bruce was saying, was that we really don't understand how far that dial has been turned. So how big a change in surface temperature we'll get with a given change in some other environmental factors. And so that makes the idea of making deliberate changes extremely risky. So I thought I'd add that here.
Okay. Let me go to a question that or a couple questions here from that we've gotten from online. First one from Twitter, from Freedom Fan, and this gets to the sort of hiatus, Bruce, that you mentioned, and one of the big processes that people have been talking about. So the question is, if the, quote, missing heat crept somewhere into the deep oceans for the past 16 years, Why didn't it also go there in the 16 years prior to that?
Good question. And the real reason is something we call natural variability or noise in the climate system. The climate system is a pretty complex nonlinear system, and there's variability. We tend to think of day-to-day weather as one type of variability, but even the climate system on time scales of years to decades has variability. You probably know about El Nino, for example, or La Nina can change year to year what's going on the planet. There's Arctic oscillation, Pacific decadal oscillation, and a lot of these are coupled ocean-atmosphere system changes that mean when the ocean circulation changes in its own noisy patterns, it can change how much of the heat gets transferred between the different sections of the ocean. So basically, our climate system has its own internal natural variability or noise, and our job as scientists to see human signals is to see them above those noise levels. And so that's why this hiatus, which is really only over about a 10-year time period, is too short a time period to see accurately relative to natural variability. It's really only when you get out to the 20, 30, 40-year time scale. There are some components of the climate system that are changing more rapidly, like the ice sheets, the Arctic sea ice, that you can actually see quickly enough in 10 years, but things like temperature, for example, there's still a large enough natural variability that, frankly, for 10 years you really can't tell much about climate change from temperature, given the other changes going on in the system.
Okay. Drew, I think I see you trying to jump in. I'm not sure we can hear you yet, but Ralph, were you about to say something to follow on that?
I was going to add something here.
Oh, wait, hold on. Go ahead, Ralph.
Bruce is making a very good point about the complexity of the system. There are many different factors that are all sort of contributing one way or another, either warming or cooling or making things wetter or drier. And when you have multiple factors involved, one has to deal with each of them quantitatively. So it's not just a matter of saying, well, one thing's going to warm and another thing's going to cool. You have to know how much. And that is something that points to the need for what we call STEM education, science, technology, engineering, and math, in order to handle those kinds of situations, or to understand multiple factors and how one has to deal with them quantitatively, how big each one is and how they compete with each other. Having a good education, a good background in science and math is extremely important. And so I think everybody here would probably agree from our own educations about how much insight that gives us into what's going on and why that's been so important also in the IPCC process.
Yeah, I think the other thing I think this brings up is, following on to Ralph's comment, is that when the IPCC looks at the climate system and tries to give us a sense of what's going on, it never is doing that in the context of a single variable alone. It's always doing it in the context of what's the entire system doing. So we have many different ways to measure, for example, ocean heat storage. We have satellites up in space measuring the energy coming in and out of the planet. We have ocean floats every few hundred kilometers of the ocean, measuring all the way down to 2,000 meters or 6,000 feet deep. We keep track of all those measurements and look at how they're all varying together, temperature, precipitation, snow cover, Arctic sea ice, and it's as you put the whole story together that you start to see where the roles of natural variability versus anthropogenic change are. So the certainty of mankind driving the system in the last 50 years primarily versus natural variability comes out of considering all of those, considering what volcanoes have been doing, considering what solar variability has been doing. It's really a sum of that whole thing, and so the STEM education that Ralph was referring to is again a focus on why the IPCC needs thousands of scientists to do this and not just 5 or 10 really bright people.
Okay. Getting to some of those changes that we have been seeing, Eric, I want to bring this back to you. Some of the numbers that really jumped out at me were looking at not just the changes that we've seen in glaciers and ice sheets, but the rate of that change and the acceleration of that change recently. So a few numbers: the Greenland ice sheet from '92 to 2001 was losing about 34 gigatons a year of ice. I think only glaciologists think in terms of gigatons, but the rest of us can imagine that that's a lot. in the following decade, from 2002 to 2011, that increased to 215 gigatons a year. Antarctica losing about 30 gigatons a year from 92 to 2001. And the following decade, that increased to 147. What in particular in the cryosphere or the ocean systems are driving the acceleration, the rapid acceleration of those changes that we're seeing in the ice sheets, Eric?
Patrick, I'll back up a little bit and mention that one of the major outcomes of AR5 has been to come up with clearer answers about what's happening in Greenland and especially in Antarctica. In AR4, there was still a lot of uncertainty about what the contribution to sea level from Antarctica was because we did not have long enough observations. And this is referring back to the comments from Bruce and Ralph that the system is fairly complex and there's not much you can say with just 10 years of data. You need a long-term record of observations. And nowadays we have nearly 20 to 30 years of observations of the ice sheets with various instruments that really come together nicely in this AR5 report. We don't have just one way to look at ice sheets. We have at least 3 or 4 different techniques looking at these complex entities and coming up with very similar answers. To put the numbers in perspective, I always use this analogy that 1 gigaton of water lost by the ice sheets into the ocean is equivalent to the consumption of water by the city of Los Angeles and its 8 million inhabitants for 1 year. So you mentioned 215 gigatons of mass loss from Greenland in the recent years. So that's basically the equivalent of the total water supply for 200 cities like Los Angeles lost by the ice sheet into the ocean, and the ice sheet is not getting that back. So in terms of the total volume content of these ice sheets, these are very small numbers. The ice sheets are only losing a little trickle of water. I get a little bit of interference here. They're only using a little trickle, but on the human scale, these amounts of water released in the ocean are fairly big, right? 200 cities like Los Angeles. In AR5, there's been an increased awareness of the important role of the ocean on the ice sheets. This is also something new compared to AR4, that we believe that in Greenland and in Antarctica, the warming of the ocean and changes in ocean circulation around the ice sheets, which are driven by changes in the wind system around the ice sheets, which are driven by the whole climate system, have had a much larger impact than what was expected in the past. I get a lot of background noise here. So this is a new element of AR5, and now there's a lot of focused research on that new aspect of ice-ocean interaction around the ice sheets that's gathering a lot of interest in the international community.
Eric, can I ask you, can you put the ice loss into terms of sea level rise and how sea level rise becomes an issue?
Yes, thank you, Ralph. The ice sheets and the mountain glaciers have contributing more and more to sea level rise. They were probably a small fraction of the total sea level rise 40, 50 years ago, and now they've become already the dominant contributor to sea level rise. The other component is the thermal expansion from the ocean, but the mountain glaciers and especially the ice sheets are contributing more and more every year to sea level, and they are really driving the curve of sea level up. And we expect that this will continue for decades, and in case of ice sheets, it could be for centuries to come.
Okay. Drew, it sounds like you were, Mike was coming live there a second. Can you hear us now, and can we hear you?
I can hear you fine. Can you hear me?
Yes, we can.
Wow, at last.
There we go. So let's just to reset a little bit, since you just returned from Stockholm and were there for the week. We've we've sort of been talking with some of the details, but you had a fairly significant role in a couple of chapters and the summary this year. So I wonder if you could, just being back from Stockholm, give us your major takeaways from the summary for policymakers and how it has changed from the previous report and what it means for us going forward.
Sure. Well, one of the things that people keep asking, actually, since the report was completed, was really what's new and what's different in this one. And I would say that that's really, well, we're not seeing things that are dramatically different than we saw in AR4, but what we are seeing is that all of the things we talked about in AR4, so that various changes would take place if emissions continue to increase, we're seeing all of that unfold in front of us now. So it's more as if we've moved to a little bit later stage where the emissions have continued to follow the highest scenarios that we had looked at in previous reports, and now we're seeing the consequences, the temperature, the snow, the ice, etc. We're seeing all these things changes as we had expected they would, but it's unfortunately all coming true just as we expected. When we look at the future, we see that these kind of changes continue, and I heard the discussion from the others, which I would fully agree with. There are still large uncertainties with aerosols, clouds. These prevent us from really constraining climate sensitivity exactly. But nonetheless, with various scenarios, we can see where in general we're going. And I think the key message there is that while many of these consequences will continue to take place no matter what, society still does have a major role to play, and that the low emission scenarios are certainly much less damaging than the high emission scenarios. So it was really an interesting process to participate in, and I think the report is really comprehensive and informative on all of these things, but it's really in many ways confirming the kind of things that have been said before by the IPCC.
Yeah.
Great.
So,
just to remind people, so 1 second, Ralph, that's Drew Schindel from Goddard Institute for Space Studies just joining us in New York. I also want to remind people that if you do want to ask questions, you can do it on the Google Plus page or the YouTube comments or on Twitter using the hashtag AskClimate. Ralph, go ahead.
So yeah, Drew was making the comment about how the scenario that we happen to be following now, based on the last 6 or 7 years of additional data, is what we call the business as usual scenario. One of the things that following one of the more conservative scenarios would do is it buys us time, because the changes would be taking place more slowly, and so that would give ecosystems and civilizations more opportunity to adjust to the changes. And one of the things we see is such rapid changes in certain attributes of the climate system, as Eric was talking about earlier, and it's much harder for us to respond as civilizations, and it's also very difficult for the flora and fauna, for the biota, to respond when things happen rapidly.
Following on that a little bit, Drew, is there an easy way to say, so let me back up a second. There are 4 different scenarios that end up with different carbon dioxide concentrations sort of at the end of the 21st century among different other different factors. Which, if you were to sort of look at our rate of increase in terms of carbon dioxide concentrations in the atmosphere now, is one of those more representative of just the rate that we're on now? Obviously, many things can change in between now and the end of the century, but is there one of those scenarios that's more accurate in terms of the rate that we are on right now?
Well, unfortunately, the rate we've been on now has been setting new records most every year, other than during the global financial downturn. But aside from that, the increase keeps growing extremely rapidly. So we tend to be on the very uppermost, that is the worst, highest emission scenario, compared to both the older set of scenarios used in previous reports and the new set of scenarios. So it's really showing that we are nowhere near the paths that we need to be on to avoid the worst consequences.
Okay, great. I'm gonna go quickly to a bunch of different questions that we've gotten from online. I don't know if some of these may be for disciplines that you aren't specialized in, so I'll just throw them out there for the group. The first question was from Jack Whitman on Twitter. He asked about the potential impact on water resources in the eastern U.S. in particular, but I'll broaden that to ask about it, I guess, sort of more around the globe. Is that something that was captured in this report? And I'm asking a bunch of atmosphere guys and a cryosphere person.
Well, the models are telling us, and this is something that either Drew or Eric might want to comment on further, they're telling us that the wet places are likely to get a bit wetter and the dry places are likely to get a whole lot drier. And that's kind of what the models seem to be saying, and that's certainly reflected in the report. The one thing that's changed since the previous report is that the confidence in that pattern has increased. And that was a point Bruce was making earlier.
Right. Okay. Jump to the next one. This is a YouTube comment from Eric Charland. Is the added fresh water from melting glaciers having an effect on the oceans in terms of acidification? And I would broaden that to say or salinity as well.
Yeah, so it's a good question. The freshwater dumping from the ice sheets has been suggested as a potential disturbance to ocean circulation. If you dump freshwater from Greenland into the North Atlantic, you may prevent the thermoline circulation from the North Atlantic to proceed. You may eventually shut down things like the Gulf Stream. And there's been a lot of work done along these lines, but I think the results from these models concur that in order for the system to be perturbed, you need to inject a lot more fresh water into the system than what we're doing right now. We call that these hosing experiments. That doesn't mean that the fresh water injected by the ice sheets into the ocean system right now do not matter. They do. But this is probably a longer-term change, a longer-term concern than something that's going to happen in the next 20 years. You probably need 10 or 100 times more freshwater dumping in the ocean to start really affecting things. But there again, this is only a matter of time, and time is the essence here in a lot of these discussions. As the other invitees on this Hangout pointed out, a lot of the observations that we have show that the Earth system is changing on a faster pace than some of the worst-case scenarios we've been looking at. And I think for the ice sheets, the change in sea ice in the polar regions, each year we have new measurements. It raises eyebrows of surprise on how fast the system can change rather than signs of content that there's some negative feedback that come to stabilize the system. The changes are sustained. There's always variability from one year to the next, but they're sustained and they're going one way.
Eric, could I ask you a follow-up question here on this, which is, you mentioned that the freshwater dumping into the ocean is probably not going to have a big effect on the ocean circulation, but what about the sea surface temperature change that's occurring?
In the proximity of the ice sheets?
Well, in general. We know that the ocean's warming.
Yeah, I think the bigger question in terms of the interaction in ice-ocean is how much the ocean is going to influence the ice sheets. That's really the way the signal is going right now. The warmer ocean is helping and contributing to the melting of the ice sheets in a complex way. We understand the basic physics, but the details are quite complex and operate on a range of time scales and spatial scales that we do not fully comprehend yet. Also, as a note to our auditor, this is a different issue from ocean acidification. Ocean acidification has to do with the uptake of CO2 in the ocean, and that's a separate issue from the freshwater dumping.
Okay. Next question, also from Twitter, and I read about this a little bit and was kind of surprised to see this. Drew, this may be a good one for you. What impact do increased levels of tropospheric ozone over urban centers have on climate? And I'll flip that around, because the part that I saw in the report was the impact that climate change might have on levels of of surface ozone in the future.
That's right. That interaction goes both ways. And urban areas, even though certainly important for most people living there now, are still a small fraction of the surface area of the Earth. So the particular value of ozone in urban levels doesn't have an enormous effect on climate. However, tropospheric ozone in general does have a large effect on climate. So in addition to having differences in the CO2 under these different scenarios, if you look at a scenario that, say, has a high emissions projected for methane, that leads to greater tropospheric ozone, and that certainly does lead to more warming in that scenario than in another scenario. The converse of this is that as climate gets warmer, generally that warmth tends to speed up reactions of the chemical reactions that lead to ozone formation in polluted areas. So you would expect that in general you would get more instances where you have stagnant conditions, heat waves, you get more episodes of very high ozone pollution.
Okay. Another question from Twitter here. Is there an alternative to reduce global warming without cutting down on emissions?
I don't think there's an easy way out. The proposals that have been put forward regarding geoengineering and things like that come with large uncertainties, and to the extent that people have been able to look at it so far, not only are there large uncertainties, but there are real possibilities that those mechanisms could either backfire and actually make conditions worse rather than better. One of the reasons for this is that the Earth is very diverse, and so any solution you try to make that might perhaps improve things in one area, you can't confine those impacts to just one area, and in other areas it will get worse. So, for example, if you put particles somewhere and it brightens up the clouds there, other changes will take place. There are no clear boundaries that the climate, that the atmosphere will respect, and the result of that will be that there can be a lot of unintended consequences.
Let me follow up on that question and tweak it in a slightly different way. Other than reducing sort of large-scale CO2 emissions, is there anything we can do in the short term with other kinds of emissions, aerosol pollution, that kind of thing, that could help to reduce or mitigate warming?
Well, generally aerosols cool the Earth under most circumstances. There are some exceptions, but in general that's what they do. So if we were to increase aerosol concentrations, then perhaps it would cool things. You were suggesting kind of the opposite, that reducing aerosol pollution in some way would cool, but that it would tend to go the other way. On the other hand, the unintended consequences of doing something deliberate like that could be devastating, and our understanding of the processes involved is really not good enough for us to be able to comment definitively in any way on what effect that would have. So I think the short answer is there's no easy way out that we know of at this point.
Well, if I could just add to that, I mean, so Ralph is just alluding to, that some aerosols warm, and those are primarily the absorbing, the black ones, which we usually call black carbon. And we just talked about tropospheric ozone and methane, one of its precursors. So certainly targeting all of those things could bring benefits in the short term and slow down the rate of climate change over the next several decades. But they don't compensate for CO2 emissions, so they're not trading one between the other. They're a separate thing, which is good to do for the sake of slowing down near-term climate, but the carbon dioxide accumulates in the atmosphere, unlike these shorter-lived things. And so really, if you want to deal with long-term climate change, which of course we should be trying to do, you have to reduce the CO2. So you can do these other things. It's a good thing to do for public health as well as climate, but it's not a substitute for action on CO2.
Yeah, Patrick, maybe one of the other things I can bring up is that there have been studies of basically trying to take CO2 out of the atmosphere, out of coal-burning power plants, smokestacks, and basically putting it in the ground, carbon sequestration. The main challenges there are really cost and technology. I mean, right now it's more costly to do that than it is to reduce emissions. So it's certainly one of the things people are looking at, but right now the most effective path certainly looks like address some of the short-term things we can, but in long term, as we were just hearing, the lifetime of carbon dioxide is basically, once it's up there, literally thousands of years, whereas aerosols will disappear in a couple of weeks. So you really can't make short-term solutions to carbon dioxide.
Right. Well, let me add one thing to what Bruce was saying. The cost of carbon sequestration, or removing carbon from the atmosphere, one of the costs is the amount of energy it takes to actually do that. And many of the mechanisms involved are not only economically costly, but they might actually be counterproductive because they take so much energy in order to actually affect the removal.
Okay, so I think we have about 10 minutes to go here. I have one more question to go from Twitter, and then maybe we can go around and you all could just kind of give closing thoughts on your biggest takeaway from the report. The question is from Detroit on Twitter. Has man over the past 150 years caused more change in the climate than all of the volcanoes, fires, storms, and weather of the past 100,000 years?
I think the answer to that is certainly no, if you look at some of the very, very largest volcanic eruptions, for example. But I'm not quite sure how valuable it is to know that answer. You know, there were ice ages, and it was a hugely different planet, right? Ice sheets came all the way down over northern North America, covered almost all of Canada, all the way down into the U.S. That's a vastly different world, but just because it can naturally happen doesn't mean it wouldn't cause a lot of hardship. Obviously, if suddenly New York was under a couple miles of ice, that's a pretty big deal. So just because natural changes can happen, it doesn't mean that they're necessarily something that we want to have happen on our planet now. Now that we have a whole bunch of systems of civilization that are all designed for the current climate, where we've had a remarkably stable climate for the last 10,000 years or so. We are adjusted to that, and so even if there are large changes, if one occurred naturally, if there was an enormous volcanic eruption tomorrow, that would still be a disaster, even though it's natural.
Or a meteor impact.
True.
Also possible. So with a few minutes then, Eric, maybe we'll start with you and go around. Just wonder what your sort of biggest takeaway point that you would want to tell people about from this report and the sort of current state of studying the Earth's polar regions.
Follow on a little bit on what Drew said. I think one of the remarkable achievements of the IPCC report with models has been to show that you cannot even explain the recent record of Earth temperature, ocean temperature, without involving human impact. So even though it's true that natural variability can be much bigger than what human society has inflicted on the climate system, the changes caused by humans on the Earth system are large enough today that we can clearly separate them from natural variability. There's no doubt in the scientific community about that. I read some interesting blog that if the confidence level was 95%, that didn't seem high enough for some of us to believe. Like there was an analogy to someone boarding a plane in an airport, and the pilot would tell them, we have 95% chance of landing at destination. You probably would not go on that plane. But for scientists, 95% confidence is just as good as it ever gets. That's a golden standard of confidence in science, and that's a remarkable achievement of these models and all these measurements.
Eric, let me stop you right there. We've got about just a few minutes left.
Okay.
So That was a good point. Ralph, let me get a quick closing thought from you, and then Bruce, since we just heard from Drew, and we'll wrap up.
Sure. Well, I think the single biggest factor in the future of climate in our system here, on our Earth, is the choices we'll make. And I think that would be the single point. The choices we'll make as a civilization about burning fossil fuels and consuming in various ways.
Okay. Great. Bruce?
Yeah, I think as you look at this IPCC report in the last few, it's very clear now that with high confidence that basically mankind is running the climate system now. It's not really being run by the natural system. We are dominating it now, and we're going to be running it as long as we're on the planet. So we have to get better at understanding the science. We have to get better at understanding how to manage responsibly the Earth's climate system as part of the environment, and not just sort of wait to see what happens. We know that the changes we're making are going to last for hundreds to thousands of years, and we could be basically setting up civilization for challenges 100 or 200 years from now that you'd have a hard time even conceiving of today to even think about them.
Okay, great. Well, I want to thank everyone out there for watching today, and I want to go through and thank our panelists again, Eric Rignot at UC Irvine and the Jet Propulsion Lab, Ralph Kahn at Goddard Space Flight Center, Drew Schindel at the Goddard Institute for Space Studies, and Bruce Wilicki at NASA's Langley Research Center. Thanks again for taking part and telling us your thoughts on the new IPCC report. And to everyone watching, if you want to continue to post your questions online using the hashtag AskClimate, we'll see how many of them we can get to, and we'll continue to answer those. So, thank you very much.